Okay, so now we're going to talk about transactions, and transactions are the mechanism by which states evolve over time. So why do we even need transactions? So I'd say the primary reason why we do is because the world is a complex environment, and often we need multiple state transitions to happen at once. A good example would be delivery versus payment transactions, whereby two parties perform an atomic swap of some cash for an asset, for instance, of a bond for some cash consideration. So we need this to happen at the same time, because we don't want one party to have the cash and the bond, or another party to have the cash and the bond. We want the swap to happen atomically at the same time. We either want it to happen or to not happen, and we introduce transactions as a mechanism that enforces that. And you can think of them as quite similar to relational database transactions, although with relational database transactions you can roll them back if they're unsuccessful halfway through, whereas with transactions in Corda, they're simply either uncommitted or committed, and we'll talk about what that means a bit later on in the slides. But for now, let's look at what a transaction is comprised of. As I said, transactions are atomic units of change to update the ledger. You can think of them as a container or a construct that take 0 or more input state references and produce 0 or more output states. Now, you wouldn't necessarily want a transaction with 0 inputs or outputs, as it doesn't update the ledger at all. So typically, you'd either have one that has 0 inputs and an output, or an output or an input and 0 outputs. And we say that what happens is, with a transaction, when an output state is created, it consumes the input state reference, and that input state that is referenced is marked as historic. So that's a very simple transaction with one input state and one output state. But there are actually 3 different types of broad transactions which can be supported, or that actually are required. And they are issuances, updates, and exits. So with an issuance, we issue states on the ledger. With an update, we change the properties in a state. So we consume the old version and produce a new version. With exits, we consume the old version and we don't create a new version, because the state is not required on the ledger anymore. It's potentially a financial instrument that has matured or expired, for instance. So let's talk about issuances. They create new states on the ledger. Of course, because they're creating a new state on the ledger, they don't contain any input state references in respect of the new state. But what they do is create one or more output states. And a typical example would be agreeing some kind of bilateral deal, like a swap, or issuing some cash on the ledger. So this S0 state here could represent some cash or a bilateral deal. And we use this grey box with the lines in it to represent a no state or no input or output state. And we use this grey box here with a marker in to represent a state that has been created on the ledger or exists on the ledger. Then we can update a state. We use updates to change state properties. And actually, a typical example here that I've got on the slide is transferring cash. How do we transfer cash to somebody in Corda? Well, what we do is we take the existing cash state and then we change the owner. So we change the current owner's public key to the proposed owner's public key. And we do that by updating the cash state object. So updates take one or more input state references and create one or more output states. So you can see here how that works. So you can see here that this S0 state references, this is actually a state reference, and it references the output state in the prior transaction. So we're going to talk a little bit about state references now. So state references comprise of a transaction ID, which is a hash of a transaction, and an index. So the transaction ID refers to the hash of the transaction which created the state being referred to, and the index references the position of the state in the outputs list. So the outputs list is indexed at 0. So for this prior transaction here, you would have as the transaction ID, you would have the hash of this transaction here, and the index would be 0 because there's only one state here. So you can think of the transaction ID index as a coordinate that can reference any state which is on the ledger. The only catch being is that you need to know which party has the transaction containing the state that you're referencing. So how does this work in practice? Let's say we have a transaction with two updates, an update to state A and state B, and then we have a subsequent update to state B that references the prior state B that was created in the prior transaction. Then the state reference for B1 is the hash of the prior transaction and the number 1 because it occurs at the second point in the outputs list. State references are very important in Corda, because when you produce your transaction, you don't actually put in the actual states themselves, you put in the references to the prior states. And then you use these references to resolve the actual prior states. So you might have to reach out to other parties and say, hey, can you please provide me the state for this transaction hash and an index number. We'll talk a bit more about that in verification consensus. Lastly, we have exits, and exits remove states from the ledger by ending the state chain. So it's pretty simple. You would consume the previous state that was created in the previous transaction and not create a new state. And this effectively exits that state off the ledger because potentially the instrument or agreement or contract is not required anymore on the ledger. But as I mentioned, crucially, you still have access to all the historical versions of that state that facilitates a useful audit trail for the life cycle of that agreement or contract or instrument. I've only really covered issuances, updates, and exits in isolation, but of course, the transaction model is pretty flexible, and if you so need, you can actually combine all of these together in the same transaction. Although you wouldn't necessarily do so, it is possible to do so. So transactions can be as complex as you need them to be to facilitate your use cases. So you can see here that we've got a transaction where a state A0 is updated to A1, and a B0 is created on the ledger. These two are consumed in a more complex transaction that gives rise to a C0 and an A2, and the B0 is then exited off ledger, and then we have the A2 is used in a transaction separately to the C0. And D4 references a transaction further back in the chain that's not on this slide. So you can think of the Corda ledger comprising of multiple transactions that reference the prior transactions by hash, with the current state of the ledger being all of the output states that have been created in transactions that have not yet been marked as historic or not yet been used in subsequent transactions. It's worth noting as well that transactions can contain many state types. There's this one here that contains cash and a bond. So it's an update transaction where cash has been updated and a bond has been updated. But what does this actually represent? So in the absence of extra information, it's worth noting that it's actually fairly difficult to, upon first glance of a Corda transaction, to ascertain what it's trying to do. So this could actually be a coupon payment on a bond, whereby the bond state has been updated to mark that the coupon for this particular quarter, for instance, has been paid, and the cash state has been updated, so the owner is being changed from the issuer of the bond to the bondholder. So obviously the bondholder is being paid the coupon. However, this could also represent a delivery versus payment transaction whereby the cash is being swapped for a bond. So this is an atomic DVP transaction where cash and the bond has been swapped. So you do need a little bit more data to explain what's going on in transactions, and that's where commands come in. So a bit later on, I believe in the next webinar, we're going to discuss what we can use to do that, and that's where commands come in. Like with Bitcoin, you can split and merge fungible states. So obviously GBP is fungible, it's cash. You can take an input cache state and split it up into multiple output states. So this transaction here on the left is characteristic of perhaps one peer on the ledger using £10 to pay for something that costs £8 and then sending the remaining £2 back to himself as change. Then of course you can take multiple inputs and then merge them to create one output. So you can actually think of Corda creating a directed acyclic graph of states as they evolve over time, as they can be split and merged. And as we've seen in the prior slides, input states always reference prior output states. So as I mentioned at the very beginning of this webinar, transactions are atomic. That means a transaction is an indivisible and irreducible set of changes. And what that means is that for the various state changes that you include in your transaction, all of them must occur, or all of them must be successful, or the transaction is not deemed to have happened. So here, if the state transition for C is correct, but A is not correct or valid for some reason, and B is valid, then we deem this whole transaction to be invalid. However, if they're all correct, then we deem the transaction to be valid. And at this point, all of the states would be consumed or marked as historic. You can view transactions as simply an atomic set of changes to update the ledger. But what we haven't done yet is introduced any control mechanism, for instance, the contract code that governs how these shared factual states should be updated. So we haven't discussed that yet, but that will be the focus of the next webinar. So we've talked about transactions, but how do we know whether a transaction actually updates the ledger or not? So before the ledger can be updated, the transaction needs to be committed, and the only way to do this is to get it signed by all the required peers. And that means that all the peers that are involved in the transaction, let's say this is a bilateral agreement representing, say, an interest rate swap, then it requires both participants to the swap, the fixed leg and the floating leg to sign this agreement. And what they do is they would take the transaction bytes and apply a digital signature over the transaction hash. And then this digital signature is appended to the transaction in a list. So transactions are only committed when they are signed by all the required peers. But actually what I've left out so far is how peers ascertain whether the transaction is actually a valid update to the ledger. And we'll cover that in the next webinar. That's where the contract code comes in. But for now, you can think of a committed transaction that has been signed by all peers, and you can think of an uncommitted transaction that has not yet been signed by all peers. So it's worth noting that actually an uncommitted transaction is merely just a proposal to update the ledger. Any party or any peer on the ledger can create a transaction proposal, and these proposals must be inspected and signed by other peers on the ledger on a need-to-know basis. So just to demonstrate very trivially that transactions are indeed proposals, you can have Alice propose a legally binding transaction for Bob to sell his house for £10. But obviously this is a silly transaction because Bob would never sell his house for £10, right? So Bob doesn't want to enter into that deal. Therefore, the proposal is never committed. It always remains uncommitted. So if Alice wants Bob to sell his house, he needs to inspect the proposal and sign it. At the point he signs it is at the point where he enters into the deal. Okay, so if he doesn't sign it, then the proposal would remain uncommitted. So we say that uncommitted transactions are just proposals to update the ledger, and it's important to remember this. If we got a transaction here that involves an IOU and some cash, what's happening here is that we have Alice paying an amount of cash to Bob. So she's actually paying £5. So she's partially settling the £10 IOU by paying £5 to Bob. So what we're doing is we're updating the amount on the IOU from £10 to £5, and then we're updating the owner on the cash from Alice to Bob. And at this moment, this transaction is uncommitted. It probably would have been proposed by Alice, as she is the one who has the cash, and she would also have this cash, and she would also have this IOU state as well. But because Alice and Bob haven't signed it yet, it's uncommitted. So what would happen is Alice would first sign. So because it's only partially signed, it's still uncommitted, and then Bob would sign. At the point where Bob signs, the transaction is now fully committed. Though it's worth noting that I am leaving out a slight detail of where uniqueness consensus provided by notary services come in. But for now, let's leave that out, and we can think of a transaction being committed if it's signed by all the required peers. So at the point where it's fully signed, then the states would be marked as historic, and the newly created states would reflect the new state of the ledger, shared by both Alice and Bob. When I mentioned that states were immutable, they're only immutable by virtue of the fact that digital signatures are applied over the transactions which create them. So these digital signatures enforce output state mutability such that it's easy for any peer on the ledger to ascertain if the states have been changed or mutated, because you have the digital signatures over the original transaction containing the original states. So, and as transactions reference prior transactions by hash, we end up with an immutable chain-like structure. Kind of looks similar to a blockchain, although in Corda, transactions are not grouped into blocks with other unrelated transactions. So this is just a quick recap point here. Committed transactions enforce output state immutability because they are digitally signed. So if you do not digitally sign your transaction, then it cannot be guaranteed to be immutable. So another party or peer on the ledger could potentially change it. Just a quick point before we finish this webinar. We got about another 5 minutes to go, and we're going to talk about transactions not being instructions. Instead, they're proposals to update the ledger. So with most other distributed ledger technology, transactions involve some kind of contract. So say in Ethereum or Fabric, for instance, you have a transaction which involves some code which must be run on all nodes machines that calculate an updated state of the ledger. And that's not what happens in Corda. Instead, what happens in Corda is you'll have one party that proposes a newly updated state of the ledger, and the other parties verify that the newly updated state of the ledger is actually valid. So you can think of Corda transactions as stating what the updates are, as opposed to how to calculate them. So you can think of Corda transactions being declarative. So we've just got a very, very quick illustration here. So this is how Ethereum or Fabric may work. So you have the current state of the ledger, which is a list. It's actually just a list here of the numbers 1, 2, 3, and 4, and we print that out here. And then what we do is we want to update the state of the ledger, and we do that by performing some calculations. So what we'd like to do here is remove the odd numbers from the list, and we want the new state of the ledger to reflect the even numbers. So what we do is we take the list, and we check to see if the numbers in the list are even. If they're not, then we remove them, and then hopefully we get to the new updated state of the ledger. And what would happen is that this here in the middle would be the smart contract, or the contract code, which is distributed to all peers on the ledger, and they all calculate the updated state of the ledger and then compare the results. If there's quorum to the required amount, then the ledger will be updated and comprise only of the even numbers in the list. However, this is not how Corda works. So how does Corda work? Instead, what happens is you will have one party that produces a proposal. So this is a new transaction proposal that will take in the current state of the ledger. So let's just assume for now that the ledger only has one state, and that's the numbers 1, 2, 3, and 4. And we say that the proposed output state is 2 and 4, so only the even numbers. Then the transaction proposer can calculate this output state in any way they like, right? Because this is simple, they can literally just write the numbers 2 and 4. However, for more complex transactions, they can use whatever algorithm they want to produce the new output states. It can be proprietary. They don't necessarily have to share this code with any other participant on the ledger. So this is just a proposal. And this proposal is distributed to other parties on the Corda network. But obviously, because proposals are uncommitted by default, we need to get all the involved parties to sign such that the proposal can be committed. So we need them to approve it. How do they do that? Well, we need to introduce this notion of a contract. And the contract here, which is just some pseudocode that looks a bit like Python, we're just saying, here's a piece of code that performs some validation over the proposed update to the ledger. So here we're saying that if there's a number in the output list that is not even, then verification fails, because we only want numbers which are even. But then if the verification doesn't fail, then the party performing the verification will sign it, and then if all have signed the transaction, then we update the ledger. So this verification is facilitated by the contract code, which we'll discuss in the next webinar, and the contract code is used to verify a transaction on a need-to-know basis. So only the parties involved in the transaction, when it's initially created, will actually run the contract code and verify. So that there won't be any unrelated third parties performing this verification. And then, assuming that the transaction proposal is valid, then the verifiers will sign it and commit it to the ledger when all the signatures have been collected, and the signatures are valid as well, of course. So this is just a silly slide, really, but it's just to drill home the point that transactions are not instructions which require action. So they're not like transactions are viewed in Ethereum or Fabric. They are actually proposals which require verification. So anyone can create a transaction proposal that can then be verified on a need-to-know basis by the required participants to that transaction. So say if I was going to send yourself some cash, then the participants would be yourself and myself. So you would want to check that cash transaction is valid, and I am indeed sending the cash to you. You'd want to check that your public key has been used as the new owner of that cash. Likewise, if we entered into a bilateral agreement, you would want to check the terms of the agreement, as would I, and thus it would require both of our signatures. So we'd both verify and we'd both sign. And only at the point where we'd both signed would the proposal be committed to the ledger, and the ledger would be updated to reflect the new transaction. So just to reiterate here, the logic to create a transaction proposal can be split from the logic to verify a transaction. So say, for example, if you want to use a proprietary valuation model to value an option or some other derivative, then of course you can do that with Corda, and you don't need to share that logic or that code with your counterparties. However, the code to verify whether the price of that option was reasonable or not would be public and would be in the contract that governs how that option state can behave over time. It would govern how it's issued and govern how it evolves and can eventually be exited off the ledger. Just to reiterate, transaction proposals require verification, and this verification is performed separately to transaction creation. So, in summary, anyone can create a transaction proposal and they're uncommitted by default, but before they are committed, they must be digitally signed and verified by all the required peers on a need-to-know basis. Verification happens via the contract code, which will be discussed in the next webinar. And once a transaction is committed, I'm missing out the notary service for now, but let's assume that the notary service has signed it as well. Then the input states will be, the referenced input states will be marked as historic, and the newly created output states reflect the updated ledger.